So we've learned about the types, the sets of real numbers. Now we're going to look a little more at how they're organized and how we can classify numbers. So this is a Venn diagram. This is a little different maybe than what you've seen. It uses rectangles instead of circles, but this is a Venn diagram. We're going to use this to help us classify numbers. We're going to start with the innermost rectangle, this innermost rectangle, and inside this we want to put the simplest set of numbers there was. What was the set that had the easiest numbers, maybe the fewest numbers, didn't get fancy? That was the natural numbers, right? If you'll recall, natural numbers are anything you can count with. So 1, 5, 1, 2, skip a few, 99, 100. Anything you can count with is a natural number. Now, after the natural numbers, we talked about the whole numbers. What made the whole numbers, the set of whole numbers, different from the set of natural numbers? Well, we added the number 0. And what you want to start seeing in this Venn diagram is the organization. The set of natural numbers is completely inside the set of whole numbers. That means every natural number is a whole number. Since it is completely inside, if it's a natural number, it's also a whole number. So 5 is a natural number, and it's a whole number. Now, what was the next set we looked at? Well, we took all the whole numbers, and we took their opposites, and that created the set of integers. So the integers include all the natural numbers, they include 0, and then they include negatives. So -7 is an integer, -35 is an integer. Again, notice the organization. Every natural number is a whole number, and every whole number is an integer. Now that does not work as we go down the graphic organizer. Not every integer is a whole number, because integers include negatives and whole numbers do not. Not every whole number is a natural number, because 0 is not a natural number. Now, after the integers, we talked about fractions. And we introduced the set of rational numbers. Remember, rational has the word ratio in it, fraction. So this includes, obviously, fractions. And it also includes 2 types of decimals. Do you remember the types of decimals that are considered rational numbers? Well, the first type are repeating decimals. Repeating decimals can be written as fractions. We will look at that at some point in class about how we write repeating decimals as fractions. They are rational numbers. The other type of decimal that is rational are terminating decimals. If they end, if it terminates, it's a rational number. Organization. Every natural number is a whole number. Every whole number is an integer. Every integer is a rational number. As you go back down, that doesn't always work. Rational numbers are not all integers, but all integers are rational numbers. So, all of these over here are one big happy family. And then we have the barrier. What's on the other side, do you think? What set is not in this diagram yet? Well, over here are your irrational numbers. And like I said, this line right here is a barrier. A number cannot be a rational number and an irrational number at the same time. It has to be one or the other. What are some examples of irrational numbers? Pi, that's the most famous one, right? Non-perfect squares. If it's not a perfect square, if you plug it in your calculator and you get a big, long, ugly decimal, it is an irrational number. Negative non-perfect squares. The negative square root of 7. 7 is not a perfect square, so its negative root is irrational. And remember, there are other decimals over here that look repeating, but they're not. So like 2, 1, 2, 1, 1, 2, 1, 1, 1, dot, dot, dot. That's not a repeating decimal. It's just got a funky little pattern to it. It is an irrational number. Now, all of these numbers are in this great big box of the real numbers. So everything, we talked about this in yesterday's notes, every number you know is a real number. If it's on the number line, it's a real number. So everything in here, rational, irrational, all the other special sets, they are all real numbers. Okay, I messed up. I forgot to put my blank notes in Google Drive, and so I'm doing this at home without my blank notes. At the bottom of your notes, there are 3 numbers, and it tells you to classify those numbers, to name all the sets to which they belong. I'm going to guess and try to remember what those numbers were. I might choose the wrong number, so you classify the numbers that are on your notes. So first of all, I think the first one is -3/4. And if we want to classify -3/4, if we want to decide what all sets it belongs to, well, we look. Is -3/4, is it a natural number? No, it's not something you count with. Is it a whole number? No. Is it an integer? No. Is it a rational number? Well, it's a fraction, so it is a rational number. So -3/4 is a rational number, and it is also a real number, because every number you know is a real number. The next number that I think I have for you to classify is the square root of 100. Now, that's a square root, but can we simplify it? We can. What is the square root of 100? It's 10. Now, where does 10 go in the diagram? Where do you think its best classification is? Its best classification is a natural number. Can you count with 10? Of course you can. That's how you learn to count. You counted to 10. So 10 is a natural number. Well, since it's a natural number, it's everything outside of that. So it's a whole number, it's an integer, and it's a rational number, and it's a real number, because everything you know is a real number. Now, the third one is the one I can't remember. So what I want you to do, I'm guessing it's irrational. Why don't you check me, classify it, and we'll check it when we'll go over the notes.